Hi, I'm happy to show you today our latest results on inverse design. Today I show you the setup where we managed to do inverse design experimentally using this whole table you see here. First, I would like to start with a very quick and brief description or explanation of what is a spin wave. And so a spin wave exists in a magnetic material where you have a net magnetization, meaning that your spins are not compensated completely in the sample, and you will have then at the end a net magnetization. And how do we measure that or excite that? I would like to start by showing you an electromagnet. So an electromagnet is controlled by a current source and a voltage source down here, and we can monitor the magnetic field using a Tesla meter. And what we do is that we apply a large enough field in order to saturate our sample, meaning that we will align all the magnetic moments in the sample in the direction of the magnetic field. So if it's going that direction, all the magnetic moments will be also pointing in that direction. And that's not yet the definition of spin wave. This is just the sample that a spin wave exists in. How do we excite a spin wave? After we saturate the sample, so we have applied a large enough field, it could be many techniques, but in this setup, we use electrical excitation. And so we need this very, very important device. It's called a vector network analyzer. And the device is special in that it both sends and detects the signal from the sample, and keeps both the magnitude and the phase of the signal that it measures and it sends. And so what happens is, let's say we're sending a signal from that direction, and we're detecting it from that direction. So it sends the signal here. It creates we use, so I didn't mention, it's a signal that has high frequency, meaning that it's in the microwave range. And so it sends this microwave range signal to that side of the sample, and creates a smaller alternating field because it is a high frequency current. So a smaller alternating field that then will disturb the alignment of the moments to the magnetic field, and it will then spin will start to precess around its axis. And because the spins have a interaction between each other, so one spin precessing will cause the next or the neighboring spins to precess as well, and then a wave will start to precess from one end of the sample to the other. And we detect it exactly the same way. So when the wave reaches the other side of the sample, we detect it using the VNA, because by it precessing, it will create an alternating field that can then be transformed into a current that can be detected by the VNA. And so we get our signal on the VNA. This is exactly how we do the measurements. I just wanted to give this brief introduction so that everybody can follow around. So what is inverse design? Before I go again into the details, inverse design is an approach that instead of so we have the direct design and inverse design. A direct design, which is the very normal design process, where you sit down, you say, I want to get a functionality that is 1, 2, 3, let's say a demultiplexer. So I will send two signals at the input, and I want to separate them at the output. And then you sit down, you do micromagnetic simulations, you do whatever you need to do in order to find this design that will satisfy your functionality that you aim for. And then you go ahead and fabricate it. Then you decide what will be your input signal, and then you measure that and hope that everything works all right in order to get your functionality. Inverse design works a bit differently. You still have your three ingredients. So you have your input signal, your design, and your output signal that you aim for. But in this case, we know our input signal and we don't know our design, but we know exactly what we want to get from the device. And so we use this output signal in order to reiterate over to find our design. And I will give you an example in order for you to understand. So how we do it here, the idea is that we want to have some kind of a design region, what we call, in order to manipulate the spin waves on the sample and keep measuring the output signal and reiterating over this experimental output signal to find the functionality that we want. How we do it here, so with spin waves, as I said, they are very sensitive to magnetic field. So we want to use that functionality of spin waves or characteristic of spin waves in order to manipulate them. And how we decided to do it in this case, by using this PCB. The PCB has our design region, and this design region consists of 7 by 7 array of current loops. So these like little tiny omegas that you see here, they are our current loops, and we want to be able to control each of them independently in a wide range of currents in order to create Ørsted field locally on the sample. So this will be put exactly on top of the yig of the sample. Doesn't matter which sample. Here we use a sample called Yttrium Iron Garnet, which is known for being a good base for Magnonics. So we put this on top of our sample, and locally we will use these Ørsted fields created by these currents in order to control the spin waves on the sample, very, very localized control. And the next, or one of the challenges, was how to control each of these independently and in a wide range. And so we worked with a company to provide us with these current sources that have, as I said, 7 by 7, so we have 49 current loops. And here we have 5 current sources. Each has 10 channels.
Let me say a few words what is actually the outcome of this fantastic device which Nora has constructed. So here you see how field distribution looks like. So it is simulated. It's very complicated field distribution, but that's the strength of the inward design, that it doesn't care actually how complicated computer will find a solution. You just need to change any properties. But for formal reasons, you can see that it creates a field. We can change field up to 5 millitesla by each such omega resonator. And at the end of the day, we have such a complicated landscape of magnetic fields which we fully control by these 49 current sources. As the results were published in January this year in this paper, so you can go for details there. And what is the main outcome? The main outcome, we wanted to get a notch filter. So what you see here is a transmission measured in experiment just between 2 antennas versus frequency. We have a region, and our task now is to keep this transmission unchanged as much as possible and to get here rejection as deep as possible. Yes, so we want to have notch filter for this frequency range of 5 megahertz. The most important in inward design is so-called objective function. It's just a scalar, it's just parameter which you measure out of experiment, and your aim is to ask computer to find such a configuration of current to maximize it or to minimize it, depending how you define it. So in some sense you convert what you want to get into mathematical language. So here it means very simple that here it should be as deep as possible, and outside it should be as unchanged as possible. Afterwards you need algorithm. Again, no details, but we tried different algorithms. This one is genetic, which is kind of like selection works if you are developing different race of dogs, for example. Very powerful tool, but any algorithm works. For example, even direct search has shown it to be very efficient. And yes, you can see how it works. The idea is very simple. You measure it once, you get objective function, you give it to computer. Computer has different algorithms which defines the next set of functions. You measure it again, and you do it as long as you will get some optimization. Let's see how it works. So here you see a current which is applied. So blue means minus 300 milliampere, some matrix, so this is 9 by 9 red means plus 300, and you can see here how current is changed, and here you can see how result is changed. And here will be number of iterations. So let's have a look. You see, this is iteration, and it slightly improves the situation. And then after 2000 of iteration, we have a rejection up to 70 dB. Let's have a look once more how it works. And you see minus 70 dB means 40 dB better than minus 30 dB. So it's 4 orders of magnitude. We improve rejection in this region by 10,000 times, which is very quite good. Okay, so that's how notch filter works. Then using the same device, Noura and Fabian, they made a demultiplexer. So they sent two frequencies, F1 and F2, to this channel, and they want to get F1 to go to output 3 and F2 to go to output 1, like it's shown here in linear regime, so linear spin waves. And what you need to do, the same device, you just change objective function. Okay, measurements took a little bit more time because you need to measure, switch between antennas and so on, but all this was correct, and here you can see the result. Again, so in principle it works like two notch filters, and you want to get that the red signal is rejected here as much as possible, and this is one antenna, and blue signal should be rejected here as much as possible. And you can see again with the same approach how it works, that it searches for the optimal solution, and then it gets like minus, I think, 80 dB here and minus 80 dB here. So quite good situation when we really can get a demultiplexer for the system. The same device was used for very different functionality, published in this paper just in May, just very recently. What Nora and Fabian did here, they shown that the same device can do nonlinear functionality. Before, all devices were linear. So they could operate with nonlinear waves, but the outcome was linear data processing. And nonlinearity is very strong. With nonlinearity, you can do logic gates, like in our computers, like CMOS is doing. You can do neuromorphic computing and many other issues. And they try to focus on logic gate. Exactly the same device, just another objective function, another functionality. Here we work on one single frequency, so everything is easier. And the whole set of logic gates has been shown. First of all, inverters, then AND, NAND logic gate, or NOR logic gate, and we finish with a half adder. Half adder is a more complicated device. It replaces something around 14 transistors in CMOS. It has two inputs, A and B, and two outputs, sum and carry. Principally, it can add up to 2 bits, so 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. And at the end, it can give you 2. That's how 2 looks like in the binary data. Very simple device, but if you can do cascading, if this output can go to the input of another, you can do any mathematics, and that's how our computers look like. Again, another objective function, that's how real field distributions looks like for the optimized case, and principally we have shown that this same approach can correct any binary data processing, so we can go now to more complicated full adder and so on tasks. Let me finish this video with just where it started and what is the status and where it goes in terms of invert design in general. So these are two first papers. So this one was developed by Wang when he was in Vienna. Now he's with professor in Wuhan, 2021, and simultaneously we did this work in parallel. It was published another paper by Adam Porat and Jerk Saba. They also used invert design, but they went for more complicated tasks like neuromorphic computing. And this was the beginning. And now field of invert design is a huge field with huge potential. Here I can show you just people who are working on invert design here in Vienna. So two groups are involved. So our group of nanomagnetism and Magnonics, and there is a group of Dieter Süß on physics of functional materials. They are focused on numerics, we are focused on experiment. And many things are going on. For example, Florian Bruckner got IMAX project where he's trying to use invert design to make super efficient antenna to excite the text speed waves. Claas Abert got Toposhai Chiral where he will try to use invert design principally to develop general to optimize concept of inverse design to make it more powerful, that it can address much more complicated tasks. We all together, with Francis, my Claas, Dieter, me, we've got this Magnonic, which we do already together with Hungarian partners, with Zenbaa and other parts, where we trying to combine inverse design with parametric pumping to amplify spin waves, not only to scatter them. And John Deep just joined this project as a postdoc. Andrii has made a set of fantastic papers on making inverse design concept stronger with the supervision of Claas, and now finishing his PhD. Fabian just started his PhD and he's continued this concept, which is you show in this video, seen in this video. Philip Boris supervisors, supporting the team, and Jason is working together with Florian on his tasks. So we see many people, many research directions. You can find more details here at these 2 web pages. We're trying to keep them actual. And my final wording would be that I really believe that inverse design has a huge potential because it can address any kind of task: RF application, binary data, neuromorphic computing, reservoir computing, sensing. It's just a super universal tool for everything, and you have full freedom how to use it, and it makes our life much easier. And at the end of the day, we can achieve with spin waves, we can fulfill such tasks which we could not do without inverse design. So it's a big added value that it can reach something which was not possible before inverse design. So we really believe the future of inverse design, and thank you for your attention.